Alright, this is Mr. Gillum, and today we're going to work on graphing some ordered pairs again, and we're going to take a look at what we call some linear graphs. Today we've been preparing for a while now because we're going to talk a little bit about bivariate data, which means that we're going to have two variables this time. Alright, but before we get too carried away though, I want to do a little reviewing. It's been a while since we've graphed on a coordinate plane, and so I want to re-talk about what a coordinate plane is and how it works. A coordinate plane is a set of two number lines, one horizontal, meaning sideways, okay, one horizontal, that direction, with 0 in the middle, of course, and the bigger numbers to the right, the smaller numbers to the left, we call him the x-axis. And there's another number line also, and that's where our second variable comes from. We call that the y-axis. And it also has a 0, but it's turned sideways, and so the positive numbers go up and the negative numbers go down. Okay, and we call him the y-axis. So we have the x-axis and the y-axis. All right, so hopefully it's kind of looking a little familiar to you. That's where our two variables are going to come from, our x variable and our y variable. An ordered pair is in the form of parentheses, where the first number tells you left and right, and the second number tells you how far up and down. So it's a way to talk about position. So when we start talking about bivariate data, instead of having equations that we can solve for a variable, like 2x plus 1 equals 3, so you can see there's only one variable, and that's x. But today we're going to have some variables that have maybe x and y, something like that, okay? And we're actually going to save the equations of the bivariate data for another day. But the two variables that we're going to be talking about will be x and y, and they're each represented by an axis. We call it bivariate data. The word bi means two. So two variables. This word here almost looks like the word variable. We're going to talk about x and y and two variables in our equations today. And I know that as we do our whiteboard warm-ups especially, I see a lot of people using these charts. We call them t-charts, and it's used to compare two values. Now because our ordered pairs are in the form x comma y, we always like to use the left-hand column as the x column and the right-hand column as the y column. It keeps our order straight so there's no confusion. Okay, our values in the t-chart are actually ordered pairs. Okay, so in our t-chart today, which is something that I know you're familiar with, instead of just thinking of them, okay, as 1 and 2, 2 and 3, 3 and 4, and looking for a pattern like that, we're actually going to graph them on a coordinate plane. This is the coordinate 1, 2, and the coordinate 2, 3, and the coordinate 3, 4. And we're going to look at what pattern it makes on the graph, okay, on the coordinate plane. A linear model is a model representing a chord plane that changes at a constant rate. That sounds kind of funny, but it changes at a constant rate, and I see the word line here. And so I would like you to write these examples down with me. I'm going to write 3 of them here. And when you think of the word linear, we have some examples here. I'm going to draw one going like this. I'm going to draw one going like this. I'm going to draw one going like this. Okay. Now, when you think of linear and changing at a constant rate, a linear model looks exactly like a line. It looks like a line. And so when I say constant rate, that means that it goes up the same amount as it goes over. Up and over never changes. The amount going up compared to the amount going over never changes. It's the same amount each time. Or it could be going down too. We would call this a negatively sloped line, but we'll learn more about that another day too. But you can see that it kind of goes, it looks like a line. It's very straight. It goes from one point to the next, and it keeps the same rate the entire time. On this last example, so we would consider this one to be linear. This would be linear. And this one would be non-linear. And if you really wanted a specific name for it, we would call this one parabolic, another math term that you will learn someday. But as you can see, it goes over and down, and the steps, like, they change. They don't look the same each time. the steps don't match all the way across. Like on this one they do. It's the same amount of change each time, so we call it linear. And it looks like a line. That doesn't hurt either. And this one doesn't look like a line because it's got curves in it, so we wouldn't call that one linear. Okay, so today part of the practice is going to be whether it's linear or not, and basically that just means if it makes a straight line. And so before we get too carried away, we're just going to do a brief review of how to graph coordinates, and I'm going to label them with the letters. So we're going to start with 3, 5, and this is the x and this is the y value. So what I'm going to start with is I'm going to move left and right 3. Now remember, this is the x-axis in the positive direction and negative direction. This is the y-axis in the positive and negative direction. So we're going to move x 3 in the positive direction, y 5 in the positive direction. So 1, 2, 3, 1, 2, 3, 4, 5. So there's where point A would lie. All right. And so it's a little harder without that visual to see where my pen is moving, but 3, 5 would be over 3 and up 5. B would be back 2 and up 4. So 1, 2, 1, 2, 3, 4. That's where B would lie. C, negative 4, negative 5, 1, 2, 3, 4, 1, 2, 2, 3, 4, 5. There's C. 6, negative 2, 1, 2, 3, 4, 5, 6, down 2. And then we're over to E, and E kind of got switched to the next line on accident, 0, 3. So these are the tricky ones. I'm moving left and right, 0, up and down 3. So left and right 0, up 3. E would actually be right there on the y-axis. Then we have 6, 0, 1, 2, 3, 4, 5, 6 to the right. In the positive direction, there's F. 0, negative 2. So again, this is tricky. Left and right first, up and down second. So left and right 0, down 2. There's G. And then H. Left and right negative 4, up and down 0. So 1, 2, 3, 4, up and down 0. There's our H's. Okay, so just a little review on how coordinate planes work and how to find the location of each point or each coordinate. And now we're going to use that information to help us plot some more real-life situations. Okay, so on a whiteboard warm-up, it might say something about how many minutes you work out compared to how many calories you burn. And what I'd like to do is I'd like to graph these points from a t-chart onto a coordinate plane to see if it is a linear model, okay, if there's a constant rate of change. One way you can tell that there's a constant rate of change is if there's a pattern in both the x and the y column, but the pattern has to increase or decrease the same amount each time. So before I graph it, I notice that this is increasing, going up by 10 in the x column each time, and it's going up by 100 in the y column each time. So before I start to graph my points, I want to make sure I have an appropriate scale. And so because I see that my x-axis is increasing by 10 each time, I'm going to remember that my x-axis is going to go up by 10, 20, 30, 40, 50, 60, 70, like so. So I'm going to write as small as I can to remind myself that that's 10, 20, 30, 40, 50, 60, 70. So I'm changing my scale a little bit. So each line represents 10, so I can fit all the numbers there. On my y-axis, I see that it's changing by 100, so I'm going to change that to 100. So 100, 200, 300, 400, 500, 600, and 700. Okay, I know it's going to be hard to see on the video, but I'm just changing the scale, so I guess it's important to listen to the volume on this part. Although these numbers are small, they're just increasing by 10, 10, 20, 30, 40, 50, 60, 70, and up and down. Since we're increasing by 100, I'm going to change my scale to 100 for each line. It'd be silly if I had to count out 100 squares up and down to represent the same thing. So, like we were talking about earlier, this t-chart actually represents ordered pairs. And so I have these ordered pairs here, 10, 100, 20, 200, 30, 300, 40, 400, 50, 500. And so in this case, this model, when I graph these points, I go over 10, up 100, x first, y second. And so over 10, up 100, that point would be right there. And then again, I look at the next point, and 20, 200, over 20, up 200. And then over 30, up 300, over 40 up 400, over 50 up 500. And so when you look at this graph here, this model of the data, you can see that it makes a pretty straight line. If you ask me, if I were to connect this line right here like so, and make a line out of it, you would see that it makes a pretty straight line. So in this case, this model I would call linear. It kind of has a pattern that it follows, and it goes in a straight line. You do need to be a little careful when you're making your line, because depending on the example, like how many minutes you work, you can't work a negative amount of minutes. You can work 0 minutes, so our graph really needs to stop at 0. When x gets to 0, there won't be any negative part to this graph in particular. But if I continue to exercise, you could probably predict how many calories I burned in 100 minutes if you wanted to, just by looking at this model and going over 100 and seeing where that line would intersect that at. You'd be able to predict where it was. So let's take a look at another T-chart here, and this one I did incorporate some negatives, and we're talking a little bit about sea level and air pressure. Okay, and so again, as I look at this, I see that this changes by about 50 each time, and this one changes by about 10 each time. So I want to make sure that my scale on my axes makes sense. So again, I'm going to label very tiny, but I'm going to label my x-axis by 50s. So it would be 50, 100, 150. In fact, I'm going to label every other one here. So that would be 100 right there, and 200 there, and each one would represent 50 each dash. And then up and down, I'm going to go by 10. So this will be 20, 40, 60. So each line represents 10 on that one. So it would take me a really long time to graph up to 100 and up to 500 squares. So now what I'm going to do is I'm going to think of these as ordered pairs. I'm going to graph them on the number line, x and then y, left and right first, up and down second. And so if the sea level was below sea level by 100, that could be feet or meters or miles or whatever it is. So back 100, so right there, and then up 40, that's where it would start at. Okay, back 100, which would be 2 tick marks to the left, and up 40, and then back 50 and up 50. Okay, so 50 would be right there. Left and right 0, up and down 60, so looks like about right there. Over 50 and up 70, right there, and then finally over 100, up 80. Okay, and as you can see again with this one, and sea level does go into the positives and negatives, and we can make a line there, and it looks to me like a line, so I would consider this to be linear. Okay, so I'll model the data on a coordinate plane and then determine whether it's linear. All right, this example, it looks like we have age to height relationship. So it looks like my ages are going up by 5s, and looks like the biggest number over here is 6.5. So let's just say we'll go up to 7. So on my x-axis, there's 2, 4, 6, and then this last one would be 7. So we're just going to go by, oh, no, sorry. Take that back. On the x-axis, we're changing by about 5. So when I want to label my x-axis, let's make it by 5, 10, 15, 20. 25, 30. So make an appropriate scale, and then on my y-axis we'll just go by ones. So that would be 1, 2, 3, 4, 5, 6. Okay, we're just going to go by ones on that axis, but it's important to change your scale appropriately. So when I graph these ordered pairs, which are represented in my T-chart here, let's see what happens. 5, 4, so over 5 up 4. And then we have 10, 5. 15 years old, you're about 6 feet tall, okay. 20 years old, uh-oh, we're only 6.5 feet tall. 25 years old, uh-oh, I'm staying the same. 30 years old, I'm still staying the same. So in this case, if I were to connect these points, uh-oh, it looks to me like, well, we're never going to be a negative age, so we could do a little arrow like that. There'd actually be an asymptote there, but you'll learn about that later. In this case, uh-oh, I don't think that's linear. It looks too curvy to me. So I would say this one would be nonlinear. Okay, and in this real life situation, that would make sense because we don't keep getting bigger and bigger and taller every single time. And so because I want to get this video a little shorter, I'm going to go ahead and label this one. We're going to go by 10s on the x-axis and 10s on the y-axis, and I'm going to label each of these ordered points. So 1070, 2060, 30-50, and 40-40. Now, even though this line looks like it's going downhill this time, it is a line, and so we would consider it to be linear. All right, so that's it for today. I hope you can tell whether the model is linear or not, and I'll see you in class.